Now, we will move to the general definition of the electric flux. Okay. So that we have an arbitrary shape of arbitrary surface. It's not necessary to be an flat surface. Okay, and we put the surface in the area with the electric field. Also, the electric field is not necessary to be constant. In this case, if we want to calculate the electric flux that passes through this area, how can we do that? Okay. We will use the concept that we used in the previous chapter, that when we have to deal with the surface or the volume that is not regular, we can divide the surface to be a very large number of small pieces, and then on each pieces we can approximate that the area is a flat area. Okay, it means that if we look at this area, we can divide it into the large number of small area like this. For example, like this. And for each small pieces of the area, we can assume that each piece is approximately a flat area. Okay, flat area. And also, on each piece, we can also approximate that on each piece, we approximate that E is a constant, because each piece, the area is quite small. So, even though we know that the electric field is not a constant, but if we look only on this piece, the change of the electric field should be very small if the area is very small. So, we can approximate that E is a constant. If this piece has the area of dA, we can also write the vector, the area vector. Here we use the symbol dA. And the electric field here on this piece is E. So we can write down that the flux on this side, on the outer side, not inner, we are interested on the outer side of the area. On the outer side, we have the electric flux d free. We use the word d because this is the electric flux only on this piece. So d free is equal to the E dot dA. Okay, d free is equal to the E dot dA. Now, if we want to calculate the flux that passes through the total area, we will define that the total flux phi E is equal to the summation of E dot dA. Okay, this is the definition of the total flux on this area. But when we do the summation like this, when dA is go to 0, we can use the technique of the integration to write down this equation as E dot dA. Okay, maybe I omit this first. This means that we sum up the flux from each piece of the area dA all around the surface, and this is the total flux. So we have the total flux is equal to the integral. Remember that the integral is nothing but the summation, right? We do the summation, it is an integral, but it is the summation of the very small pieces, but the large number of the very small pieces. So we have that. This is the general definition of the flux on the general surface. Okay.